Hey everyone, it's Mr. Anderson coming to you again with a section from our CPM Common Core Algebra ebook. Today we're going to talk about section 6.2.4, and we're going to try to get to the bottom of what it means when we've done some calculating of a least squares regression line or an LSRL model. What kinds of things can we communicate? How can we do that? Because remember, we can do a lot of math and we can have computers do a lot of the math for us. But as we work and continue to grow in this subset of math called statistics, one of the hardest jobs we have is communicating our findings to others. And I don't care what kind of research you do. I don't care what kind of results you find. If you can't explain it and make it meaningful to other people, you're not a very good researcher or statistician, right? You've got to make it understandable to people who in general don't understand stats and sometimes maybe even fear stats, okay? And that's our job today. All right. Although correlation coefficient is widely used to describe the amount of scatter in a linear relationship or a linear association, we talk about the correlation R being strength. Unfortunately, it's an arbitrary computation, right? Correlation does not have a real-world meaning. In this lesson, we're going to learn a way to make sense in context of that correlation coefficient. We actually have to I have a hiccup. We have to modify R slightly and come up with a new descriptor, and that new descriptor is going to be very, 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 very useful for us. So I've got problem 6-91 here. And we did a little work with a problem like this one already. And what I hope you take away from this, and as we continue to apply this to the next problem, is a sentence frame. And that sentence frame should be pretty gosh darn meaningful in allowing you to communicate these findings to someone else, right? If you had to explain it, or if you had to defend it, or if you had to present it, right? In lesson 6.1.3, Karen discovered that a human's height is associated with their forearm length. Karen is curious whether height is also associated with foot size. So remember, we had the anthropologist who found the skeletal remains, and we did a little work with the ulna length, right? And now Karen is investigating, is there a relationship between height and foot size or shoe size? And of course, we're using the U.S. Equivalent of shoe sizing to give us some quantitative data for this. So you're going to see those shoe sizes in the, I guess, left part, right? And I've got a kind of a side-by-side stack here. You can see my arrow continuing. And then, of course, the height in centimeters over there on the right, or to the right of the shoe sizes. Those things that say checksum are there in case you needed to validate that you'd entered your data correctly. We won't be needing those today. So it wasn't practical, for Karen to measure all her classmates' feet. So Karen collected the following shoe size data from her classmates. And we're going to go ahead and goof around with this using the E tool on Desmos. But before we do that, let me just make mention of this is a giant limitation in statistics. We often run out of time or other resources that don't allow us to collect all the information we'd like to have in order to make the most accurate model. And as we grow in our CPM courses or into a stats course, we're going to figure out what makes good data collection happen. Before we do that, we've got to check out what this looks like on our eTool. So I'm in my CPM ebook. I am in 624, and I've got the eTool right here in 6-91. Okay, so I can click on that, it pulls it up, and there you go. Oops, I zoomed out, sorry about that. I can see all the data, and honestly, it looks pretty gosh darn good. I see, the reason we've got like little vertical stacks here is because multiple classmates have the same shoe size, maybe just slightly different heights. And this is looking pretty good. It looks like a linear model would be a pretty gosh darn good fit. I don't see any obvious curvature. So yeah, I think we're doing okay. And here's all that data that has already been entered. Okay. In a previous lesson, and I'll show you again in a subsequent lesson, how to get this LSRL in there to show up. But I can just, I can click on it to make it appear, right? It shows up in blue. And I can even plot my residuals. This is a built-in feature in Desmos once I give Desmos that language that I wanted to see it. I've got the equation, y equals 3.96788 x plus 131.232, right, if I want that. But here's my residuals, and I can scroll down and I can see them. And when I zoom in on that residual plot, I mean, I really don't see an obvious pattern or obvious curvatures in that residual plot. It looks reasonably randomly scattered, so I think a least squares regression line is going to be appropriate here. I can go ahead and turn that back off. I can click up here to turn those residuals off. Oops, excuse me. And then I can go back down here and I can look at the graph again. Okay, but the question or some of the metrics we're going to need here are still contained down here because there's something that we've already talked about. We've already talked about this R value. This R equals 0.8617. And I'll just turn this back on. That's a pretty gosh darn strong positive linear correlation or linear relationship because that R value is high. It's pretty close to 1. Okay, it's not perfect, but it's pretty strong. Okay, meaning my model is a good model. But we've also got this other thing, and this is the thing that I care about right now, this R squared value. And that's what we're going to go ahead and tackle in our or we're going to use to tackle the how do I explain this to other people. So I've got, like I said, this blue sentence frame already pre-populated, and here's what I tell students to do. First and foremost, copy this R value as a decimal. And I already forgot what it was. It was 0.7424. Okay. 0.7424. Notice that is the R squared value, not the R value. They are definitely related. One is just the square of the other, or one is the square root of the other, depending on which direction you're going, but they are not the same thing. And after we do that, I tell students to turn that into a percentage, right? And of course, you turn a number into a percentage by multiplying it by 100 and then round to the nearest whole percentage point. Okay, so here we go. If I take 0.7424, that's going to be 74.24%, which is about equal to 74%. Okay, this is the number I want. And you're going, Anderson, you crazy coconut. Why? Why we had to do all that work to get that? People understand percentages. Okay, remember, your job as somebody who's explaining this and going to try to make this meaningful is to make it as easy as possible on your audience. Make it digestible. Okay, that way he or she can put a mental grip on some of these things. Okay, so here we go. This means that, and you can always use this blue sentence frame that we've got right here. And I'm gonna help you fill it in, and then you're gonna be able to take it and apply it wherever you want. This means that 74% of the variability, meaning the amount of fluctuation we see in our model, or the amount those residuals deviate from that x-axis, or the amount we are off by, the variability in my first variable, okay? Nope, I don't even want to say my first variable because that's not accurate. My response variable, my y variable, the thing I'm trying to predict, human height, right? Because that's what Karen is going after for here, okay? And I'm going to mark this up like the context, right? The variable I'm predicting. Okay, so it's going to be your y, or your response variable. All right, this means that 74% of the variability in human height can be explained by our LSRL model, or a linear, let's say a linear relationship with shoe size. And this is, of course, in context, This is our explanatory variable, or our x variable. Okay? And this sentence here is what we're going to use to explain this relationship in context. And folks, the higher that r squared value, the better job our model does. Okay? If it's closer to 100%, whoa, we've got a pretty good model that's doing a great job in a strong relationship. If it's closer to 0%, right? Maybe don't want to use that. And you saw one of the first things I did here, folks. You saw me evaluate this, make sure there was no obvious curvature or outliers in my data. And that's one of those steps that we got to take and visually assess or visually inspect ahead of time, right? If 74% of that variability is explained, what about the rest of it, okay? And that's the question I lead you with here in B. It says, if only a portion of the variability in height can be explained by shoe size, what other factors might go into determining someone's height? Well, check this out. 74% is explained. That means we still have, that means we still have 26% unaccounted for. And the other 26% variability might be due to things like genetics, maybe diet, maybe disease, maybe broken legs, maybe steroids, right? All of those other things that could affect growth and height. All of those things are going to fall into that other 26%. Okay? Anything else that might account for someone's height being not in line with our model, right? There you go. Okay? All right, let's check out number 6-97 now. And ladies and gentlemen, initially on the surface, this problem looks like the exact same. So I copied and I pasted our same sentence frame here. And you might be thinking, well, Anderson, I've got to take that r value, I've got to square it to get the r squared value. And normally I'd applaud that. Okay, but check this out. Let me read with you this problem. Let's talk about why this may not be the best approach for this type of question. Check it out. Suppose you found that the correlation between life expectancy of citizens in a nation and the average number of TVs in the household in that nation is R equals 0.89. That's a pretty strong positive correlation, right? Does this mean that watching TV helps you live longer? And some of you guys are probably shouting at your computer screens right now, and you're probably saying no. And remember back to where we've come from and what we've done. Association is not the same thing as causation. And what that means, let me remind you, is that just because two variables are related does not mean that one causes the other. Because think about it, right? How long would we be living, especially in like modern America, if you just got to watch Netflix and then live your longest life ever? No, that's not how it works, right? We know that being sedentary causes our life to be significantly shortened, right? But what's the deal? What could be happening here? Well, wealthier nations are probably more likely to have more televisions in the household. And because those nations are wealthy, they probably have things like first world healthcare. And first world healthcare is definitely something that could cause you to live a longer life, right? So when you run into a problem like this, if you can immediately say, hey, I've got no relationship here. I'm sorry, I've got a relationship, but I've got no causal relationship here. Then start to look for that lurking variable, that variable that might be out there influencing something to appear to be happening. Okay, because that's exactly what's going on here in 6-97, right? It's not the TVs causing people to live longer. It's probably the fact that they are living in a wealthy nation. And that wealthy nation means they can afford TVs and afford premium healthcare. Okay? Couple review preview problems here for you guys, right? It is not a straight shot. It's 99, 101, 102, and 104. Let's give these things a shot, and let's make sure we're asking the questions that come up when we're trying these review preview problems. Ladies and gentlemen, thank you for watching. Have a great day.